Welcome to this explainer. Okay, I want you to just clear your mind for a second and imagine we're stepping into a mathematical dojo, because today we are entering the rigorous training grounds of machine learning algorithms. We're going to look under the hood and really explore the exact mathematical martial arts required to train a machine to understand data. So get ready, because we are getting hands-on with the actual math that makes artificial intelligence possible.
Now, it's a pretty profound question, isn't it? Can calculus teach a machine how to learn? I want you to challenge yourself right now to see the math we're about to cover, not as a series of dry, boring equations on a chalkboard, but as the ultimate dynamic training regime for our algorithm. Think of calculus as the coach, pushing our model to be faster, sharper, and way more accurate.
So meet our protagonist. It's a basic linear regression model, and its main goal is to find the perfect straight line right through a scatter of data points. You can see those green data points here, and that gray line? It's trying its absolute best to slice right through the middle of them. But check out those vertical orange dotted lines. Those right there are the residual errors. Basically, it's the distance between the actual data and what our model predicted. Our algorithm's very first challenge, really its ultimate quest, is to minimize those dotted lines. We want to squash them down as close to zero as mathematically possible.
Section 1. The analytical strike, ordinary least squares. To absolutely conquer those residual errors, we're introducing our first technique, which is essentially a direct algebraic strike designed to perfectly solve the error in a single calculated move. Okay, let's dive into this step by step. First, we have to define our enemy, right? That's the cost function, specifically the sum of squared errors. We actually square the residuals we just saw to ensure negative and positive errors don't just cancel each other out. Second, we unleash the calculus. We take the partial derivatives of this cost function with respect to our line slope, which is m, and its intercept, b. Third, by setting those derivatives to exactly zero, we are mathematically demanding the absolute lowest point of error. And finally, we solve that system of equations for m and b. Just like that, in one swift, elegant set of algebraic steps, we've derived the absolute best-fitting line. No trial and error needed.
Just let this sink in for a second. Ordinary least squares computes the best fit line by minimizing the sum of squared errors using a direct algebraic solution. It finds the exact values of coefficients analytically without iteration. I mean, it's so powerful because it requires literally no guessing. It is just pure, precise analytical perfection.
Section 2. Measuring power levels. Evaluation metrics.
All right, so once we draw our line, how do we prove it's actually, any good? Well, here we have two distinct ways to measure our model's error. Mean absolute error simply averages out the raw distance of our mistakes, but mean squared error squares those differences before averaging them. Now, what's really interesting about this slide is how MSC fundamentally changes the algorithm's behavior. Because we are squaring the errors, a small mistake stays small, but a massive mistake? That becomes exponentially huge. MSC harshly punishes the algorithm for wildly missing a data point, which forces it to be far more precise and way more cautious about extreme outliers.
And then we have R squared. You can kind of think of R squared as the ultimate measure of our model's power level. It essentially tells us what percentage of the data's behavior our model actually understands, ranging from 0 to 1. A score of 0? Well, that means our algorithm has learned absolutely nothing. But an R-squared score closer to 1 means our model has achieved absolute mastery over predicting the data.
Section 3. The grinding regime, gradient descent.
But here's the catch. What happens when the dataset is absolutely massive? I mean, when we're dealing with millions of features, that one-hit analytical strike of ordinary least squares becomes computationally impossible. The computer simply cannot do the algebra fast enough. That is exactly when our algorithm has to endure a grueling, iterative training montage. Here's the mathematical training manual for this technique. If you look at the gradient descent algorithm update rules, you'll see the model updates its parameters, w and b, by subtracting the partial derivative of the cost function. But I want you to notice that little alpha symbol. That is the learning rate. And the crucial point here is that alpha dictates the size of the algorithm's step. If alpha is too big, the algorithm might leap right over the correct answer. But if the step size is too small, it's going to take an absolute eternity to finish training.
Let's try to visualize this physical intuition for a moment. Imagine the cost function is this giant bowl, and our goal is to reach the very bottom, where the error is lowest. Now, if our current position has a positive slope, meaning we're on the right side of the bowl looking up, the calculus derivative is a positive number. So, by subtracting a positive number, our algorithm steps backward. It decrements the weight, safely sliding down the valley of error to the left.
And this brilliantly illustrates the exact opposite scenario. What if we're stuck on the left side of the bowl? Well, the slope is pointing downwards. It's a negative gradient. So when the algorithm subtracts a negative number, it's actually adding to the weight. It steps forward, incrementing its value, pushing down the slope toward the right. It is always hunting for that ultimate minimum objective at the bottom.
So, step by step, iteration by iteration, the algorithm just grinds through the data. You can really see the model taking those incremental jumps here, relentlessly following the downward slope of the gradient. It might take hundreds, maybe even thousands of steps, but it never gives up until it converges, eventually conquering the curve and achieving absolute minimal loss.
This quote perfectly captures the ultimate payoff of our training montage. Gradient descent is an iterative optimization algorithm that adjusts model parameters gradually to minimize the cost, using the slope, or gradient of the cost function, to update weights step by step toward the minimum. We've basically taken a machine, given it a totally random starting point, and through the sheer power of calculus and iteration, it has successfully learned to navigate the rugged terrain of error to find the optimal solution, entirely on its own.
Section 4. The ultimate form. Polynomial regression.
Okay, so our algorithm has mastered the straight line. Fantastic. But let's be real. In the real world, data is rarely that simple, right? It presents a serious dilemma. What happens when our basic straight line just cuts awkwardly right through a beautiful curve of data points? The residual errors would be massive. The calculus we've learned so far would be practically useless if we restrict ourselves to just one dimension. We desperately need a way to literally bend the line to our will.
Wow, look at this visual transformation. By unlocking higher mathematical dimensions, our model's line actually curves to flawlessly track the nonlinear data. Notice the equation right over there in the pink box. We didn't just throw away our linear regression. No, we evolved it. We took our feature, let's call it size for a second, and we added a brand new parameter, size squared. By feeding the algorithm squared or even cubed versions of the exact same data, we are allowing it to map highly complex, curved relationships. It's a real game changer.
But as always, with great power comes incredible risk. Expanding our feature vector to include x squared and x cubed means our numbers can just explode out of control. Think about it. If your original size feature goes up to 1,000, well, size squared is 1,000,000 and size cubed is a staggering 1 billion. Our algorithm will completely destabilize if it tries to compare the number 1 to 1 billion. Therefore, before we can safely use polynomial regression, we absolutely must apply strict feature scaling. We have to shrink everything down to a manageable uniform scale. Absolute discipline is required to wield this power.
So through ordinary least squares, gradient descent, and polynomial regression, we have successfully mastered the math required to absolutely conquer our training data. We can fit a line to almost anything now. But what happens when our algorithm finally steps out of the dojo and faces unseen data in the unpredictable real world? Have we trained it perfectly, or have we made it so obsessed with the training data that it completely fails at reality? Well, that, my friends, is the highly dangerous trap of overfitting, and it is a battle for our next explainer. See you then.